Have you ever gazed at the majestic peak of Mount Rainier, towering over the Pacific Northwest like a snow-capped sentinel? At 14,411 feet, it's the highest mountain in Washington state and one of the most iconic landmarks in the United States. But beneath its serene, glacier-draped exterior lies a volatile secret. Unlike many volcanoes that erupt dramatically from their summits, spewing ash and lava skyward, Mount Rainier has a peculiar habit. It tends to blow its sides rather than its top. This strange truth isn't just a geological quirk, it's a story of weakened rock, hidden pressures, and catastrophic collapses that could reshape entire landscapes. Today, we're diving into the science behind why Mount Rainier behaves this way, exploring its history, the forces at play, and what it means for the future. To understand Rainier's odd eruption style, we first need to know what kind of volcano it is. Mount Rainier is a stratovolcano, part of the Cascade volcanic arc, which stretches from northern California to British Columbia. These volcanoes form where the Juan de Fuca plate subducts beneath the North American plate, melting rock into magma that rises to the surface. Stratovolcanoes like Rainier are built from layers of lava flows, ash, and volcanic debris, creating steep conical shapes. They're known for explosive eruptions, thanks to their sticky gas-rich magma that traps pressure until it bursts. Think of Mount Fuji in Japan or Mount Vesuvius in Italy, classics that often vent from the top. But Rainier deviates from this script. Its eruptions are more likely to involve lateral blasts, where the explosion rips out from the flank rather than the summit. Why? The answer lies in a process called hydrothermal alteration. Deep beneath the mountain, magma heats groundwater, creating a network of hot springs, steam vents, and acidic fluids. These fluids percolate through the rock, chemically altering it over thousands of years. Minerals in the volcanic rock react with the acids, turning solid andesite, a common rock type in Rainier, into weak, clay-like materials. This weakening is most pronounced on the upper flanks and summit where the hydrothermal activity is intense. Imagine building a sandcastle with wet sand. It holds shape at first, but as water soaks in and alters the structure, it becomes prone to slumping. This alteration makes Rainier's edifice unstable, setting the stage for sector collapses. A sector collapse is when a large chunk of the volcano's flank gives way, sliding downslope in a massive landslide. When this happens, the sudden decompression can trigger an explosive lateral blast, directing the eruption sideways with devastating force. It's like uncorking a shaken soda bottle from the side. The pressure releases horizontally, blasting out rock, ash, and superheated gases at speeds over 300 miles per hour. This isn't hypothetical, it's happened before at Rainier and similar volcanoes. Let's travel back in time to one of Rainier's most dramatic events, the Osceola Mudflow, around 5,600 years ago. During this catastrophe, the northeast flank of the mountain collapsed, removing about 1,600 feet from the summit and creating a horseshoe-shaped crater over a mile wide. What caused it? Scientists believe hydrothermal weakening played a key role. Combined with the weight of massive glaciers, Rainier hosts more glacial ice than any other peak in the contiguous U.S., with 26 named glaciers covering about 35 square miles. The collapse unleashed a debris avalanche that transformed into a lahar, a fast-moving slurry of water, mud, rock, and volcanic debris. This lahar raced down the White River Valley, covering 212 square miles and reaching as far as Puget Sound, over 60 miles away. Deposits from this event are still visible today, buried under modern towns like Enumclaw and Buckley. But the Osceola wasn't a one-off. Rainier has experienced at least 11 major lahars in the last 6,000 years, many linked to sector collapses. Take the Electron Mudflow, about 500 years ago, which originated from a collapse on the west flank and buried parts of the Puyallup River Valley under 30 feet of debris. These events often don't require a full-blown eruption. Sometimes magma intrusion bulges the flank or an earthquake shakes the weakened rock loose. When the side gives way, any pent-up magma or gas can explode laterally, amplifying the destruction. For a modern parallel, look no further than Mount St. Helens, just 50 miles southwest of Rainier. In 1980, St. Helens underwent a similar process. Hydrothermal alteration and magma injection caused the north flank to bulge outward by 450 feet before it collapsed in the largest landslide in recorded history. The resulting lateral blast flattened 230 square miles of forest, killing 57 people and sending ash across the continent. St. Helens and Rainier share the same geological DNA. Both are Cascade stratovolcanoes with extensive hydrothermal systems and glaciers. If Rainier follows suit, a lateral blast could devastate areas within a 180-degree arc, hurling ballistic rocks miles away and generating pyroclastic flows that incinerate everything in their path. So what signs indicate Rainier might be gearing up for such an event? The mountain isn't dormant, it's active, with the last small eruptions occurring in the 19th century. Fumaroles, steam vents in the summit craters, release gases like carbon dioxide and hydrogen sulfide, keeping parts of the ice free despite sub-zero temperatures. This heat has carved the world's largest volcanic glacier cave system, with over 2 miles of passages inside the ice. Seismic activity is constant, with up to 5 earthquakes per month near the summit, often caused by fluid movement rather than tectonic shifts. The U.S. Geological Survey monitors these with seismometers, GPS stations, and gas sensors, watching for increased activity that could signal magma rising. The U.S. Geological Survey monitors these with seismometers, GPS stations, and gas sensors, watching for increased activity that could signal magma rising. The risks are immense because Rainier looms over densely populated areas. Over 150,000 people live on ancient lahar deposits in the Puget lowland, including suburbs of Tacoma and Seattle. A major sector collapse could generate a lahar larger than Osceola, racing at 40 miles per hour and reaching Puget Sound in under 2 hours. It could dam rivers, cause flooding, and even trigger tsunamis in the Sound. Economic damage could top $40 billion, disrupting ports, highways, and power grids. To mitigate this, the Mount Rainier Volcano Lahar Warning System, installed in 1998, includes acoustic sensors to detect incoming flows and sirens to alert communities. Annual drills prepare residents, but evacuation would be a race against time. This strange truth about Rainier, blowing its sides due to weakened flanks, highlights how volcanoes aren't one-size-fits-all. While some, like Hawaii's shield volcanoes, ooze lava gently from the top, stratovolcanoes like Rainier evolve through cycles of building and destruction. Hydrothermal alteration acts like a slow poison, eroding stability from within, making lateral failures more likely than summit blowouts. It's a reminder of Earth's dynamic power and the need for vigilance. As we admire Rainier's beauty from afar, let's appreciate the science that unravels its mysteries. Monitoring technology gives us hope. We can predict and prepare. But nature always holds surprises. If Rainier stirs again, its side-blowing tendency could rewrite the landscape once more. Thanks for joining this exploration of one of the world's most enigmatic volcanoes. If you enjoyed this, subscribe for more deep dives into Earth's wonders. Until next time, stay curious and stay safe.